What is up, you guys? It's Max here, and in this video we're going to solve number of 1 bits in Python. So for the problem description, we need to return, given an unsigned integer, the number of 1 bits it has. So that's also known as the Hamming weight. And we've done previously this problem named Hamming distance, and it uses a lot of the same concepts. So if you haven't checked that out, I highly encourage that you do. I'm going to leave a link to the GitHub repository in the description below if you'd like to see the code afterwards. So as we could see in this example, we have an integer, and in binary is represented like so. And there are 3 bits where there's a 1, so we'd output 3. And the same goes here. There's only 1 bit in this binary representation that is a 1, so we'd output 1. And so I'm going to break this video into 2 parts. The first one is going to be whiteboarding, and the second one is I'm going to kind of debug and go through and show you how we code it in Python. So for high level, I'm going to take a quick example and kind of walk you through how we'd solve this. So for this example, let's say we were given the integer 3. And 3 in binary is represented like so. We have in the 2 to the 0's place, we have a 1. The 2 to the 1's place, we have a 1. And the 2 to the 2's place, we have a 0. So that together would be 2 to the 0, we have something, so that's 1. And 2 to the 1, we have something, so that's 2. And we add those together, and we get 3. So now that we have the representation, we have to figure out, well, how do we count the number of 1s in this binary representation? Well, I'm going to tell you. There is a good trick that we can use, and it is the AND operator. And what that does is going to evaluate the lowest bit of this integer, and we can then use the AND operator and say, hey, is the last bit equal to 1? And if so, we'd want to increase our weight by 1. We want to increment it. So for this right here, we check, hey, is the last bit equal to 1? And in this case, it is. So we would increment weight. Now, how would we keep counting the rest of the 1s? Because if we never do anything to this integer, it's always going to stay the same. Well, we can use another bitwise operation, which is called a right shift. So let's say this is n, right? If we took n and shifted to the right by 1, then it would get changed into this integer, 1. As you could see, we've kind of just see this 1 right here. We kind of pushed it out of bounds, and it basically got pushed, and we pushed another 0 onto this. We kind of removed this guy, and we pushed a 0 here. So we shifted everything to the right one. And so that in binary is just 1, because we only have 1 in the 2 to the 0's place, so we just have 1. And this is obviously 0. So we then perform our check again. Hey, is the last bit equal to a 1? And it is, so we'd increment our weight again. We'd then perform another shift operation, and then we'd only be looping while n is greater than 0. And as you could see, because once it hits 0, there are no more 1s in our integer, so we'd want to stop. And right here, we have pretty much, we would break out of the loop. And as you can see, our Hamming weight is 2, and that is correct because there are only 2 1s in this integer. And just looking at a high level, you could see that it keeps just pushing the 1s, it keeps shifting over that integer until there's no 1s left whatsoever. So we'd catch all of the 1s that were in the binary representation of the unsigned integer. So to give you a debrief on the code, so here, as you can see, we have this solution class, and we have this method, Hamming weight, where we take in an integer n, and we're going to return an integer, which will be the Hamming weight. We make an instance of that class down here on line 11, and then we are calling, we're printing the result of, we're calling the method with this integer 3. So this is exactly the example that we took, and I'm actually going to split screen this because it'll make it a lot more obvious. So I placed a breakpoint on line 3, and I'm going to kind of debug through this a little bit. It's working its magic a little bit. Let's see. Okay, we've reached the breakpoint. All right, so you see we passed in n is equal to 3. And let's get a little more visibility over here. n is equal to 3, so you could see that this is the binary representation we're dealing with right now. We'd kind of go through our program. We have this while loop. While n is greater than 0, we want to check the lowest bit and say, hey, are you equal to 1? And if so, we would increment weight. And true is just 1 in binary, so we'd increment weight by 1 since this is going to evaluate to true. So as you can see, it got incremented because the lowest bit is 1 in this case. And then we do the right shift. And when we do the right shift, we're changing the bits of that integer. So it's going to turn into, n is going to turn into 1. Ready? So we shift the bits. Now n is 1 because we shifted the bits over to the right one. We then perform another check. Hey, is our lowest bit equal to 1? Yep, it is. So increment weight. We shift the bits over again. Now the binary representation of that integer is 0. So we break out of our loop and we return the weight. And that's pretty much it. I hope you enjoyed that video. And I hope to see you guys in the next one. All right, peace.